This is Dr. Anima Upadhyay, and today I will be talking about the factors affecting the rate of corrosion. In one of my previous lectures on the electrochemical corrosion, I have explained what is corrosion and what makes the metal gets corroded. On the metal, when it is exposed to the atmosphere, it undergoes slow oxidation due to the formation of tiny galvanic cells all over the surface of the metal. So we can say that the corrosion is due to the nature of the metal and the environment that surrounds it. On this basis, we can classify the factors into primary factors and secondary factors. The type of metals and their position in the electrochemical series are termed as primary factors, and the environmental conditions to which the metals are exposed are termed under secondary factors. Primary factors include electrode potential, ratio of anode to cathodic area, nature of corrosion product, polarization of the anode and cathode, and hydrogen overvoltage. Secondary factors include temperature, pH, conductivity, humidity, and presence of impurities in the environment. Let us start with the primary factors. An electrode potential plays an important role in determining the rate of corrosion. So let us start with the electrode potential. Electrode potential can be explained as the capacity or the capability of a metal to undergo oxidation or reduction. When two dissimilar metals are in contact with each other, then the metal with the higher reduction potential forms the cathode, and the one with the low reduction potential becomes the anode and starts suffering corrosion. Let us explain it with the help of examples of zinc and copper, or iron and copper. Now, zinc and iron are at a lower reduction potential of minus 0.76 volts and minus 0.44 volts respectively, whereas copper is at a higher reduction potential of 0.34 volts. In such cases, zinc and iron becomes anode and copper becomes the cathode. So, if we want to avoid the corrosion, the contact of such dissimilar metals should be avoided. Second important factor is the ratio of anodic to cathodic area. The anodic and cathodic areas plays important role in determining the rate of corrosion. If the cathodic area is very large compared to the anodic area, then the large cathodic area demands more number of electrons from a small anodic area, leading to its fast dissolution, resulting into intense corrosion. On the contrary, a small cathodic area demands less number of electrons, and this diminishes the rate of corrosion. To explain the anodic and cathodic areas, let us take the example of tinned iron plates and galvanized sheets. Tin is cathodic to iron. If iron is coated with tin and a scratch is formed on such a plate, then the exposed iron, which is anodic to the tin, forms the anode and the large tint surface forms the cathode. So the small anode starts dissolving very fast, becoming a big hole from the scratch to a large hole. On the contrary, if a galvanized sheet of iron is scratched at some point, then zinc is anodic to the iron. So the large anodic surface diminishes the rate of corrosion because the cathode, which is the exposed iron surface, demands very less electrons from the large anode. So if we want to prevent a metal from corrosion, the base metal should be coated with a metal anodic to it. This is further illustrated with the help of these figures. Here the tinned iron plate is shown. The tinned portion is shown with the blue, and a small scratch here, which is the anode, a small anode is formed, is shown. This scratch is becoming a large hole because of the large demand of electrons by this large cathodic surface from this small anode, resulting to intense corrosion on the tinned surface. Whereas in this galvanized sheet of iron, the small scratch which is formed is the small cathode, because zinc is anodic to iron. Therefore, this large surface, red surface shown by the zinc plating, forms the anode. Anode is very large compared to the small cathode. So it leads to very little or no corrosion on the galvanized sheets. The next important factor is the nature of the corrosion product. We all know that corrosion is slow oxidation of the metal. Oxidation results into the formation of oxides. So the product of oxidation is the oxide layer on the surface of the metal. If this oxide layer is soluble, non-uniform, porous and conducting, then such oxide layers results into intense corrosion, because these oxide layers, if soluble in nature, dissolves, exposing the metal below it for further corrosion. If there are pores on the oxide layer, then these pores also allow the atmosphere to reach the metal below it. And this is the reason oxides of iron and zinc are highly destructive oxides. But if the oxide layer formed is insoluble, non-porous, uniform, with low ionic conductivity, then such oxide layers prevents further corrosion, making the metal passive. And this is the reason oxides of aluminium, chromium and titanium are called as protective oxides. The oxides of tantalum, zirconium and molybdenum are not only protective in nature but also self-repairing oxides. Polarization of the electrodes, that is anode and cathode, also plays a determining role in the rate of corrosion. Polarization is slight change in the potential of the electrode due to the slow movement of ions from the solution towards the electrode, which slows down the current. And as a result, the rate of corrosion also slows down. So, polarization of anode and cathode results into the diminution of the rate of corrosion. Hydrogen overvoltage. It also plays an important role because it is related with the release of hydrogen at the cathode. when the metal is exposed to the acidic atmosphere, the hydrogen is evolved at the cathode and this results into the corrosion of the metal. If the hydrogen overvoltage is high, then the evolution of hydrogen is slowed and this results in slowing down in the rate of corrosion. So we can say that if we make the hydrogen overvoltage high, the rate of corrosion can be slowed down, and to achieve this, the precautions can be taken such as lowering of the temperature, smoothing of the surface of the metals, or use of inhibitors. Because at high temperature, the hydrogen overvoltage is low and the evolution of hydrogen is high, resulting into intense corrosion. Coming to the secondary factors, which includes temperature and pH. Temperature, we have already discussed, plays an important role because at high temperatures, the hydrogen overvoltage is very low, leading to intense corrosion. The dissolution of metal is fast. The mobility of ions is very fast. So, temperature is very important, and if it is low, then the corrosion can be minimized. Similarly, pH also plays an important role. pH is explained as the negative logarithm of hydrogen ion concentration. At low pH, the acid concentration is high and corrosion is also inversely proportional to the pH. So, when the pH is low, the corrosion is high. At pH above 10, the corrosion of iron is almost nil. But with a pH less than 3, the iron suffers severe corrosion, even in the de-aerated atmosphere. Although between pH 3 to 10, the corrosion of iron takes place in the presence of air. Conductivity and humidity also plays important roles in determining the rate of corrosion. Conductivity is described as the movement of ions towards the electrodes. At high conductivity, the metals suffer severe corrosion, and this is the reason. If the metal is exposed to saline water or seawater, it suffers intense corrosion. But when the same metal is kept in the fresh or the river water, it suffers very little corrosion. Humidity is another important factor to determine the rate of corrosion. Higher the humidity, more is the rate of corrosion. The iron suffers excessive corrosion at a high humidity of more than 60%. But less than 60%, the rusting of iron is slowed down, and this is the reason 60% is termed as the critical humidity for iron. Gases and particles are other important factors. If the gases are there in the form of acidic gases such as sulfur dioxide and hydrogen sulfide, they are highly corrosive and the metals rust very fast in these gases. Similarly, if the particles are present in the atmosphere and in the presence of these acidic gases, the particles, even the charcoal which is inactive, gets activated and makes the metal rust very fast. So we can conclude that if proper care and understanding of the factors are taken, then the life of the machinery can be increased many folds.